So today's last topic is all about how to measure the vastness of space. Yesterday we discussed topics like what a comet is, what a meteoroid is, what all the planets are. We discussed asteroids. We discussed how stars are formed. Okay. One of the things that we mentioned is the idea of the telescope. And that's where I want to begin today's lesson. It wasn't until the 1600s when they finally had a telescope that the worldview changed as to what space really looked like. Okay. Before that, they had a theory. They thought that the Earth was at the center and that everything revolved around the Earth, a geocentric model. Very selfish, honestly. Very arrogant to be like, we are so important that the only way this could work is if we're at the middle because we are important, right? That was actually the mindset. And when the telescope was discovered and developed, I guess, not discovered, yes. When the telescope was discovered, it really changed the worldview. And it was Nicholas Copernicus that had a theory that the sun was in the middle and that everything went around the sun, including Earth being planet 3 from the sun, right? That still wasn't fully correct, though. And it wasn't until telescopes were discovered that two different scientists, one was named Johannes Kepler, and the other one was Tycho Brahe. These two guys, they did meticulous notes, studying planets and stars and anything they could find in the sky, and they kept track of these things for years. And this was their job. It wasn't a hobby anymore. They every single night would have gone out and looked and plotted what they could see. They plotted what they found, and they made one big change. They said, yes, we think the Earth still goes around the sun, but rather than it being in circles, I actually didn't draw it too bad, but it's more of an ellipse, which is like an oval shape. And they realized the sun is at one of the focal points, and it actually has a little bit of lopsidedness to it. And why was that important? Chris, why is that little difference so important? It turned it into a science. What makes something science? The ability to make predictions that are actually right. Okay. I can make a prediction that tomorrow it's going to rain. It may or may not rain, right? And that's what makes weather actually sometimes a challenging science because we might not always be correct. But if I were to ask you what happens if I let go of this pencil, every single time I let go of this pencil, I should be able to tell you that it's going to fall due to gravity, right? And that's the hallmark of a science, right? And so we had in our slides on the previous day the idea that as soon as Kepler and Brahe were able to figure out these sorts of motions in elliptical patterns, they were able to, with exquisite accuracy, tell exactly when Jupiter would show up again. They would see Jupiter for a couple of days, and then it would be gone. And they'd be able to say, I know when it's coming back. It's coming back on May 21st. And lo and behold, May 21st it was back, right? That's what made it science, which is really cute, which is really cool. So what we're going to start by discussing here today then is the tools and technologies that allowed scientists in the past as well as today to eventually measure space and to be able to make these predictions. And so I've got a few examples on here. I don't need you to memorize them, but they had things like something called the quadrant, the astrolabe, and the cross staff. Different sorts of tools here that, I got to be honest, I don't even know how the first two work. The cross staff kind of looks like a tool where it measures an angle to the sun or to the moon or something like that, but it's really this one right here. It was the telescope. That's what changed everything because you could see something magnified and zoomed in. All these three tools seem to do is measure angles and distances between things, but this actually allowed you to zoom in and get a better picture. So here are some things I need you guys to be able to work with. And I expect this to be on your PAT. So that's why I'm kind of suggesting if you've got notes printed off or you're following along, put a little star next to this. There are a few different ways that we measure distances. You guys okay here? Okay, make it work. If I were to ask you how far it is from here to Calgary, sometimes we measure that in hours, actually. Sometimes when I ask you how far it is, you'd say it's about 2 hours. Anyone ever measure a distance in hours before? They ask you, how far is it to Colehurst? I said, it's about 10 minutes to Colehurst. No, I didn't say how long it is to Colehurst. I said, how far is it to Colehurst, right? So sometimes we measure distance in time. Sometimes we measure it in kilometers. Like I would say, how far is it to Calgary? You might say 200 kilometers, give or take. How far is it to Colehurst? 10 kilometers. Right. Well, space is so big, you can't even measure. So we've actually defined this thing. It's called an astronomical unit, and it's been given the abbreviation AU, astronomical unit. And here's basically how it works. From the Earth to the Sun is 1. However far it is from the Earth to the Sun is 1 astronomical unit, which means that we're basically just comparing based on that like reference frame. So for example, even though it's 150 million kilometers to our sun, we would say that like Neptune, what is that number down there? Neptune is 30, yeah. So what does that mean? It means that it is 30 times further from the sun to Neptune as it is from the sun to the Earth. What planets then are going to have an AU value less than 1? Less than 1. Venus and Mercury. Because those are the two planets that are closer to the sun than us. So they're going to have an AU value less than 1. Mars might have an AU value of 2, because it's twice as far as it is from the Earth to the sun as Mars to the sun. Or you can see Jupiter here, I believe it's a 5 value. So if you were to go from the Earth to the sun, or from Jupiter to the sun, it's just 5 times more. So an AU value doesn't actually tell you how far it is, but it's all about this concept. It's the idea of a reference point. It tells you in comparison how far things are. So that is one unit that you guys need to know how to be able to kind of measure. I can really foresee a question where it would ask you based on the following chart. So maybe I'll make a chart here. This is Mystery Planet. Mystery Planet. Planet X, Y, Z, and W. I should have gone in a different order. And that gives you the AUs. I tell you it has an AU value of 0.7, of 7, of 18, or of 2,000. If I were to ask you which of the following planets is no longer in our solar system, it would be planet W, because it is really, really far away, right? Or if I were to ask you which mystery planet could be Venus, then you'd say planet X. If I were to ask you which mystery planet could be Saturn, maybe that would be planet Y. I think that's in the ballpark there. What was Saturn again? Okay, Saturn was 10, so I guess I was guessing. So I can see that being a question you could get asked. Now, that's actually not the only way we measure distances, though. The other one is more common. You've probably heard of this before. It's called a light year. And I have a lot of words on the slide here that you guys can read. Let me just give you the highlights here. A light year is still a measure of distance. And it's similar in a way to how when I ask you how far is it from here to Calgary, you say 2 hours. But like, remember, hours is a distance measure of time. Well, here's how a light year works. A light year is how far light would travel if you gave it a year, which is a long ways. Okay. Imagine that I turned the lights to the room on and off. How long did it take the light to get from the light bulb to you? Like fractions of a second. Does anybody know how long it takes? Actually, it's on the slide here, so I guess I can't ask the question. If you didn't know, it takes about 8 minutes for light to get to us from the sun. That's how far away the sun is. It takes 8 minutes, which is actually like relatively short distance. Most of the stars that we look at, the light coming from those stars is at least 25,000 years old, because that is how long it takes for light to travel that far. And light travels incredibly fast. It is the fastest known thing we know in physics in terms of how fast it can travel. It is 300,000 kilometers per second. 300,000 kilometers per second. Okay, let's just like put this into context here. 300 kilometers, just 300 kilometers would get you to Red Deer probably, give or take. A little bit longer than that. Calgary's about 200 something kilometers. Red Deer's in the 400 kilometers. So imagine that you were traveling somewhere between Calgary and Red Deer. Well, that would be in a second. Except we're not talking 300 kilometers, we're talking 300,000 kilometers. So now what we're telling you to do is go from here to Red Deer 1,000 times in a second. It is unfathomably fast how fast light travels. Number to it, it's right here. It's 9.5 trillion kilometers in a year. That's how far light will travel in a year. So whenever we discuss the term light year, it's basically 10 trillion kilometers. That's what a light year is. And it's actually not a measure of time, it's a measure of distance, because it's how far you're able to go in that amount of time. For a little bit of perspective then, the closest star to Earth after our sun is called Proxima Centauri, and it is 4 light years away, which means that light would need to travel for 4 years to get here from that star. Now, when we talk a little bit about eventually humans wanting to travel in outer space, and the idea of Star Trek and Star Wars and warp speeds and hyperdrives and all of that cool stuff, even if we could travel at the fastest speed we believe things can travel at, which is the speed of light, it would still take 4 years to make this trip. I get frustrated in the car when I take my daughters on a 2-hour road trip. I usually have to give my little kids an iPad so they don't fight with each other in the back of the car. Any of you guys fight with your siblings in the back of the car sometimes on a road trip? And your parents are like, if you don't behave, I'm going to turn this car around. Can you imagine being on a 4-year road trip? That is how long it would take you to get somewhere if you were traveling the speed of light, which is as fast as we believe things travel. That's one of the reasons why, although we think space travel might become possible one day, we know there's serious challenges, because it's going to take a long time. I threw this slide on here just for some context. This is just a picture of the night sky. All of the light that we are seeing from those stars is at least years old, if not thousands of years old. Many of these stars that we're seeing, they might no longer exist. They might have turned into supernovas or red giants. They might have died in the time it's now taken for its light to get here. That is how far away they are. Like I said, the closest star that we found, 4 light years away. 4 years for its light to get here. Some stars are 250,000 light years away. Those stars have definitely died in that time frame. Isn't that crazy? Measuring the vastness of space is incredible. Now, we can measure distance and how far away we believe these things are. We also can try to measure where they are located as well. And I want to begin this topic here by discussing how we measure things on Earth. On Earth, when we measure direction, we always use these directions: north, south, east, and west. Right? Most of you guys should be fairly familiar with this, right? North is usually up, and south is usually down based on our perspectives. And we can also measure things based on latitude and longitude. And I pulled the Wikipedia page up for Lethbridge. If you haven't seen this before, Lethbridge is located at about 49 degrees north. If you can't see that, it's 49 degrees north and about 112 degrees west. Do you guys know what they mean west and north of? You guys ever heard this before? Yeah, so what is the, if I were to draw a picture of the Earth like this here, and then this is the North Pole where Santa lives, this is the South Pole, what do we call the line that goes right through the middle? Do you guys know? Yeah, okay, so the equator. So we are 49 degrees north of the equator. Oh goodness, equator. Do you guys know what the number assigned to the equator is, what value it's given? 0. And what's the value assigned to the North Pole? 90. 90. So 49 degrees north means that we are basically halfway between the North Pole and the South Pole, give or take. Okay. The 112 degrees west is based on something called the prime meridian, if you haven't heard that before. And it basically goes right through a town in England called Greenwich. More or less it's through London, England, give or take. And so if you can kind of picture a picture of the world, if this is over here, this is North America, and this is Europe over here, we've defined the prime meridian to be 0, and we are 112 degrees west of that. Okay. How many degrees total is there from the equator? Do you guys know? Technically, it's 360 all the way around, but we actually do 180 because we go 180 degrees to the west and 180 degrees to the east. Yeah, you're right, though. It is 360 total. We just label it up to 180. So 180 degrees is actually known as the International Dateline, and it runs somewhere through the Pacific Ocean. So that's how we measure. Stay with me, guys. That's how we measure things on our Earth. But space is tricky. Space is in 3 dimensions. So we need to have 2 measurements, azimuth and altitude. Okay. So let me describe to you how those work in this next picture here. Azimuth is basically what we've just talked about as your north, south, east, and west. Azimuth is basically north 30 degrees west, where what it means is that, actually this should be east based on this picture. Let me draw this a little bit better here. Based on this picture, what you would say is that you're mostly going north, but it's being tilted about 30 degrees towards the east. And we might give it some sort of bearing along those lines like that. And that's like what we do on Earth, like a northeast sort of system. The one that's new is the altitude. The altitude is basically how high up in the air you need to look at it to see. And it's based on a number system as well, going all the way up to 90 degrees. 90 degrees would be straight overhead. So I'm going to do some demos here with, you just have to look at me with where I'm at here. So imagine that I was laying on my back looking up at the stars in the sky. Right? What I might be able to do is from where I'm standing, if I see a star way over there, first thing I would have to do is like point straight ahead and then measure off to the side and figure out like what angle is that. And so from where I'm standing, that angle might be south. Or that angle might be, if I was this way here, it might be east. Or if I was this way, it might be west, right? Depending on which way I'm actually standing and orientating myself, okay, you have to figure out that part too. But then there's also like the up factor. If the star is just over the horizon, it has an altitude of like 1 or 2 degrees. But if the star is literally right above me and I'm looking at it like this, it's at 90 degrees. What if the star is behind me? Well, then I should actually be turning around, and rather than the star being north compared to me, if the star is not there, but it's like there, turn around. Well, now the star. So what you have to measure is both the side-to-side angles as well as the up and down angles. Okay. Now, if the star is literally right overhead, if you were laying flat on your back up at the night sky and the star was directly above you, we say that it's at its zenith, however you pronounce that one. And that is where it's right overhead. So this is a little tricky for you to kind of imagine. So I've got another picture here that hopefully will help explain it. Hopefully this one will work. Imagine that there's a person right here sitting in a chair, and there's a star up here in the sky that they're looking at. Okay. Let's do altitude first. Okay. If you can kind of imagine a dome is almost always how we try to draw this, so that you can kind of picture it. Imagine like a big dome, just like if you're at like a planetarium. The first thing you'd want to do is measure where north, south, east, and west are, so that you can figure out from where this person is right here, what direction is it? And I would say this star right here is in the northeast quadrant. Here, it would be in the northwest quadrant. Now, if the star was kind of like on the front side of the dome, remember how this is like in 3 dimensions here, right? If the star was like on this front of the dome, like right up here, it would be on the west south corner. And if it was on the front end of the dome over here, it would be in the southeast corner. But this star seems to be, I'm showing you it on the back side of the dome, so it's on the northeast side. So we would give you a measurement like northeast, probably something like this. From north. And hypothetically, let's say that that angle was 40 degrees. You would say that it's north 40 degrees to the east. That's how you might phrase that. The second thing you'd want to do, though, is imagine you had a rocking chair. How much tilt do you need to look up at it? And that's the altitude, and that's this angle here going up and down. And so if the side-to-side angle is 40 degrees, maybe the tilt angle, which would be this angle right here, maybe that angle would be 30 degrees. So you have an azimuth and an altitude as a way of trying to figure out where the stars are. Good question. No, they won't. You don't have to actually measure something along those lines. We could, right? I mean, that's what we'd probably need to use these tools here for. So let me go back to the beginning. Remember these tools we discussed here about like the cross staff and these guys? They were to help trying to measure the up and the over components here. And we could try to measure that. We're not going to. But yeah, in theory, astronomers would. Okay. I do need you to be able to tell me what quadrant it's in, though. Okay. If, for example, it was back here, say the star was back here in this quadrant right here, you would not say that the altitude was like over 90 degrees. Can you see how maybe I've drawn an angle like this, and this is an angle of like 100 degrees? You would never say that though, because what you would do instead is rather than this person facing towards the east, they would then just face towards the west instead, and then the angle's actually right here instead. Can I try that one more time? Here. Let me stand right here. Here's the projector. Okay. So here's the projector right overhead. Okay. Let's say that I'm standing right here. Okay. From me to the projector, what sort of angle do you expect there to be from me to that projector overhead? Is it a small angle or a big angle? Actually, it's a really big angle because it's almost right overhead. This is about maybe 70 degrees. And as I get closer and closer and closer to it, now it's 90 degrees, 80, 70, 60, right? What if I were to be way at the back of the classroom here? Well, now that I'm way at the back of the classroom, the angle's more like 20 degrees. So as it gets further and further overhead, as the star gets higher and higher, eventually it gets to this point here where it's basically 90 degrees straight up. Okay? So if I were to stand right here, it would be an angle like this, and this might be to my north. But if I were to go over to here, it might also have a steep angle, but now it's to my south, depending on which way I'm facing. If I'm facing this way, or if I'm facing this way, it makes a difference. Okay. I've actually got a practice question on our assignment, but since I'm getting some funny looks, let's do that practice. Right here together. Assignments. Calgary. So I'm going to try to draw a bit of view. Here's Calgary. The star. I'll draw a really good star. I'll draw that as a star. There's a star. Describe it. It's right overhead. So, dome. Dome. There's the top of the dome. If that kind of helps. This is right above Calgary right here. The question asks, how would the altitude and azimuth be different for observatories like Lethbridge? Compared to Calgary, where's Lethbridge? Yeah. So why don't we say that this is north, with me? Here, which direction is this? Yeah, more or less north probably. It's going to be a bit different. If I were to draw this angle from Lethbridge, you need to draw like a triangle where there's an angle here now, 20 or 30 degrees in the sky, because now that you're the star is going to appear to be north of it, and there needs to be a bit of a tilt angle to it from there. So Lethbridge sees this star, the north. But Edmonton is way up. Skills here, but Edmonton is way up here. So for Edmonton, they're seeing the star. They're seeing it's behind them. If I stand here, it's this way. But if somebody else is over here, they see it that way. Right? So it totally depends on your perspective. Somebody else is going to see it this way. And somebody else is going to see it this way. And the closer you are to it, the steeper the angle. Right? And so I might see a star way in the horizon over there, and somebody else sees it right overhead, because it depends on where in the world they are. Okay, why don't I move on? I'm going to try to maybe make like a manipulative, something that we can do in 3 dimensions to help with this, because it's really hard for me to explain it like with my whiteboard here. So if you want me to explain this more, I'll do this in small groups perhaps, and I'll actually try to do like a physical model right there in front of you to help illustrate it. So let's move on. The next thing we need to discuss are the terms triangle, ways that we measure distances. Just so you guys know, we're not going to actually have to do this, but you have to know. So here's how triangulation works. Imagine that you had to measure how far it was to this tree. We can't physically go to the tree because it's too far away, because it's like light years away in outer space. But what you can do is have somebody over here measure the distance. Well, what you do is you have 2 people measure. You see how this person, they see the tree on their left, or on their right. This person here, they see the tree on their left. It's the same thing as that star. Seabass, focus, guys. If you're not going to pay attention, I may as well send you away. It's our last lesson. For crying out loud, pay attention. This is like the person in Edmonton. This is the person in Lethbridge, and they each see the thing from a different perspective. This person sees it that direction. This person sees it from that perspective. So what you end up doing is you measure the distance between the 2 of them. You measure this distance right here. Measures an angle to the star. This person over here measures an angle to the star, and using some geometry, which you guys don't know how to do, which is fine. We're not asking you to do the math, but using some geometry, distance here, this distance here, and that's called triangulation. You really just need 3 things. How far apart the 2 observers are. They have to be in like different angle between them, which is why you can kind of see why a tool like this would have been useful, because all this person right here is doing is measuring angle. Calculate distances through geometry. Okay. Here's a classic picture of it. We're not going to do that. Let's say you want to figure out how far away the boat is, but you can't actually run a measuring tape from here to that boat, right? You measure person A and person B, and you measure how far it is. This is called the baseline. Oh, good. Okay. This person right here measures the angle between the other person and the boat. And you can actually do some math, which we cover in grade 10 and 11. So you guys will learn how to do this one day, but you don't have to do it right now. That's one thing. The second method that we can use to try to calculate objects is through a concept called parallax. And parallax basically refers to differences in perspectives. Okay? When I am looking at an object from 2 different places, sometimes the order changes. And this is the classic example right here. You guys can hold your thumb up in the air, and then like cover something up with your thumb, something small. Like I'm going to cover up Kaylin's water bottle right there with my thumb. And I'm going to look through my left eye. I'm not going to move my thumb. Now I'm going to change eyes. I'm going to look through my other eye. And all of a sudden, I can now see the object that was once hidden. Right? Take an object, close one eye, and like cover up that object. Don't move your thumb. Open up the other eye instead, and now you can see the object. Yeah, it's basically what the eye doctor does. So here's how this matters then. Here, looking at object star right here. Stay with me, guys, please. This person right here, imagine that they were looking at a background, and the background was like, say, a French flag. It's red, white, and blue, okay? This person right here, stay with me, guys. This person right here would see the star in front of the blue image, because you can see how the star is right in front of the blue, right? But this person right here, they have a different perspective. And so they can see the star in front of the red image. We call that parallax. And so we can actually do a calculation about how far it is from here to here. We can actually calculate that distance as well using geometry based on this principle of parallax, where different sides see different things. It's honestly the exact same principle as the stars. Okay? From here to me to the projector, I see the projector going this way. Right? But like Alexa has a different perspective of the projector. I see the projector in line with the board. You see the projector in line with my posters on the wall, right? Everyone has a slightly different perspective in terms of what order it comes in. So here's how this kind of works. For parallax, what we end up doing is we try to and you try to find a closer star that you know is between them, because the light years are a little bit shorter. The baseline is now Earth's two locations based on it being in different seasons. This could be Earth in the winter and in the summer. And so in the summertime, you measure what it looks like to this star from here based on a close star, and you see this pattern this way right here. And then the Earth takes half of a year, 6 months, to go to a farther away location. Now that your perspective has changed, now you see a different star in the background. Based on that and some angles, we can actually calculate how far it is there. Again, you're not going to do this math. Okay? You don't have to do a calculation. All you have to understand is how they take these measurements. They recognize that the picture from here looks different than the picture from here. Let me give you one more example of how this works. If I were to look right here at just how the order of people works, I would say, first I see Gabby, then I see Sophia, then I see Brooke, then I see Angus. That's kind of my order here, from left to right. But all of you guys, you don't see that same perspective. If I go from left to right, like I said, Brooke, Angus. Right? But what is your perspective? From left to right, you see them 1, 2, 3, 4 this way, right? Your perspective is 1, 2, 3. Like, it depends on where you are. And that's basically the same concept here. If you see a different order, just like this picture here, if you move from here to here, you see red, white, blue with a star, but this person right here sees the star in front of the red. So that's called parallax. I don't need you to do any calculations, just know how they work. Like, know what you're talking about. Okay. Last, what things are made of on these faraway planets or faraway stars? Through something called a fingerprint. It's a very unique sort of bands of light, and it has to do with prisms. If you guys have seen a prism before, when you shoot light through a prism, it spreads it into different colors. Okay. Well, different elements give off different colors. Hydrogen gives off a color spectrum that looks something like this. And what's unique about it is that there are some black lines on it right here. And helium gives off its own unique color spectrum. And there's some based on shooting this through a prism. And so we can actually tell what different things are made of based on their different chemical propositions, I guess. This is the sun right here. I can now predict what the sun is made of. Because you see how this band right here, there seems to be one of those right there. And this band right here, there seems to be one of those right there. And this band, there seems to be one right there. Apparently, there is hydrogen in the sun, which actually we knew already. We talked about that last day. So based on these like fingerprint spectrums, we can actually calculate what we believe faraway suns and stars are made of. And it's like a matching game. So, okay, let's talk about something that is not found in the sun. Calcium. I know that calcium is not found in the sun because there is a band, and there's not a corresponding one in the sun. There's also some bands right there that are not found there. So I know that calcium is not found in our sun. Okay. But I do know hydrogen is, because all of the hydrogen bands I had right here, I found a corresponding one. So we call this a spectrum. Well, because what we do is we measure hydrogen, what hydrogen looks like on Earth. This is the emission pattern that hydrogen has when we measure it on Earth, and then we compare it to what the sun looks like, and we piece it together. So we kind of assume that the elements on Earth are what the elements are in the sun. Okay, last one. We're almost done here. There's also a final way that we can tell things called a Doppler shift. And this picture here kind of helps explain a phenomenon that I'm sure you're familiar with. It's usually done with an ambulance. When you hear an ambulance go by, usually it has like a and it like changes pitch as the thing goes past you. You ever heard like the of like a car going past you? That kind of sound? What you're hearing in that kind of sound I'm making there is called a Doppler shift. And this picture helps illustrate it. As the ambulance or an object is traveling towards somebody, what ends up happening is all of the sound waves that are emitting from it, they get really squished together, and it makes it have a higher sound. So it goes, and it kind of goes from high to low. Whereas a person that it's leaving, what ends up happening is the sound waves spread out, and it has a lower pitch. And you've probably heard this before as like a car with a siren goes by you. Light works in the exact same way. Light will either have compressed or stretched out waves. Only light isn't something you hear, light is something that you see. So here's what I need you guys to memorize. Put a big star next to this. This is like another like Chris's guarantee on a test question. Always look red slightly. Blue. In a similar way to an ambulance coming towards you, having a higher pitch, an ambulance is moving away from you having a lower pitch. I've actually got a picture I want to show you. This faraway galaxy looks slightly red. Emitting red light, call a red shift. And off this last slide right here, red-looking things usually means they are moving away from us. So we believe that this galaxy here is moving away. And the other reason why we can tell this is they're not matching up exactly perfectly. We expect them to be. They're all being moved, side being the red. Red, R, right, R. A shift to the right, a red shift, means away from us, we believe. It's known as a blue shift, and that's what this last slide here discusses. The original source right here. Can you see how those same bands that were on A, how they've been shifted this way in B? We call it, which means, but that over here, it's been moved this way away from the Earth. So we can actually tell whether or not they're getting closer to us or further away from us based on their, fellas, almost done, guys, whether or not really red or blue tinge to them. And like I said, we can actually see galaxies that look either red or blue, which is kind of cool. The last thing I want you to know here is the idea of a continuous. The continuous spectrum is what this light would look like if all of it existed. But we normally work with these absorption spectrums where there's these little black lines right here that are missing. You might be wondering, well, why are those little black lines missing? And the reason why is that they're the opposite of what's found in what we call an emission spectrum. The exact same lines right here are the ones that we're missing from the one above. So if you ever see this terminology, an absorption spectrum is where it's missing little black lines. The emission spectrum is the one where it has those colors that have been missed. Now, I don't really care which one we use. What I need you to think is, could you figure out what objects are made out of? So if I were to tell you sun, could you narrow it down and tell me that calcium clearly hydrogen's lines right here, they all see that? That's one thing. The second thing you might be asked, shifted either to the left or but it's getting closer or further. Just need to memorize it. A shift to the right, which is red, means things are getting further. To the left, which is blue, means things are getting closer. Not which way planets are moving. Okay. The last slide I have here just reminds you of how we get all these colors. They're all part of the, Clayton, almost done, please. They're all part of what we call red, orange, yellow, green, blue, purple side of it. Is on this side over here. This is further away. And purple is closer. And one of the ways that I can memorize that is that these waves over here are getting closer to each other, further away. And maybe this will help, because I know you guys have done this supposedly last year in grade 8. You're supposed to learn electromagnetic spectrum. So if you remember this, maybe that's a good way of trying to memorize this. Okay, let me summarize and then we're done. Today we talked about ways of measuring space. We physically can't go out to space yet, not that far. It would take us years and years and years to. And yet we know a lot about space through indirect measurement. One, we know how to measure distance, either by what we call the astronomical unit, AU, or by what we call a light year. I need you guys to know that stuff. Two, we've also learned how to measure the great distances in space based on some angles. The two words we learned were triangulation and parallax. Triangulation is where you basically have a baseline and people measure some angles and they each have a different perspective, right? For example, everyone who's on the left-hand side of the room over here, you're seeing the projector that way. Everybody over here on the right-hand side of the room, you're seeing the projector this way. You each have a different perspective. We could actually calculate how far it is to the board based on angles from different perspectives. The exact same principle happens in parallax. You also need to know how to measure azimuth and altitude. Azimuth is basically the side to side, but it depends on where you are. From me to that projector, it's like south. But from Reese to the projector, it's east. And from Kayla to the projector, it's west. And from the whiteboard to the projector, it's north. It depends on where you're standing, right? Depending on where you are, it changes your perspective. Okay, which way is north? Let's see. North is like that side over there, give or take, right? So from me to the projector is north of me, right? But if I now stand over here, now the projector is south of me, right? Whichever way it is. I think north is more or less, that's the north side that way, right? Because Whoop Up's right along there. So it's over there? Okay, so let's do it properly. We say north is this way. So from here, this projector is north of me. But now that I stand over here, did the projector move? I moved, but now it's south of me, right? So that is azimuth. Altitude then is how steep it is. Right here, it's very steep. It's like 80 degrees up. I'm almost right underneath it. But if I stand way back here, well, now it's not quite so steep anymore, right? The further away you get changes your altitude. Okay. And then the last thing I need you guys to know is how we calculate what stuff is made of in outer space. And those are those spectral fingerprints that were on the previous slide. Let me just scroll back to it. These are our spectral fingerprints. And we can use these as a clue to figure out what stuff is like. We measure what one of these looks like from a star, and then we measure it compared to what we know stuff looks like on Earth, and it helps us figure out whether a star is made of hydrogen or helium or sodium or whatever's inside of it. What questions do you guys have? Questions? Did you know some of this stuff already? Some of it should have been new. Okay. Now, I have some good news. This is not one of the overly difficult sections. Most kids usually find the space section to be one of the easier ones. Today, tomorrow, Friday, I need you guys to work on a few things, though. I know it's almost Christmas. I talked about the idea of perseverance and grit, though. Some of the skills I want you guys to build. I know we're almost done. There's only half an hour left in class here. But I need you guys to start working on that assignment. And then tomorrow, we're going to work on that assignment. Plus, we're going to talk about a case study. The idea of, should we spend billions of dollars on traveling into outer space? So like I always do, guys, I'm going to let you have free time. Don't waste it. Use it to start this assignment. Sound good? Okay, that's all I've got. You guys are free to go somewhere if you want. Use your time well.